They showed us a universe that already seemed to be underway. That difference matters more than it sounds. A strange object can always be explained away. A bad measurement can be corrected. A spectacular headline can dissolve the moment spectroscopy arrives, and the redshift turns out to be smaller, the mass lighter, the claim less dramatic. That has happened before, and it will happen again. Webb is not revealing a cartoon crisis where every shocking image overturns physics by sunrise. The real pressure is colder than that. It comes from the possibility that even after the mistakes are removed, even after the photometric mirages are filtered out, too many early systems may still be growing up too fast for the old story to feel comfortable. And comfort is not a scientific standard, but it is often the feeling a successful model gives us. Successful models make reality seem narratable. They compress chaos into sequence. First this, then this, then this. The standard picture of the young cosmos had that kind of power. It did not claim the first billion years were simple. They were violent, dark, and full of competing processes, but they were still legible. Structure emerged step by step. Gravity gathered matter. Small things formed first. Larger things came later. Light slowly carved its way out of darkness. However exotic the ingredients, the growth itself felt orderly. Webb did not break that order in one stroke. It did something more destabilizing. It found reasons to ask whether the order had been too smooth in our minds. Picture what astronomers were trying to see. Not stars nearby, sharp and bright, but photons that had been travelling toward us for more than 13 billion years. Ancient light, stretched by cosmic expansion until the visible universe's first brilliance arrived in infrared. Webb was built for precisely this purpose, to catch the weak red afterglow of formation itself, to look through distance and effectively look through time, to watch the universe near the edge of its own beginning. NASA describes Webb's infrared capability as essential for studying the first galaxies, because the expansion of space shifts their early light out of the visible range and into longer wavelengths. That is the official version. The physical version feels stranger. You point a telescope into what looks like darkness. You hold it there. Hours pass, then days. The black field begins to fill, not with emptiness corrected, but with history surfacing, smears, arcs, red points, thin distortions made by gravity itself, and among them, objects whose light left when the universe should still have been struggling to become complicated at all. The shock was never just brightness. Brightness alone can mislead. It was the implication behind the brightness, mass, structure, maturity. In some cases, even signs that star formation had already surged and changed state unusually early. Webb's observations have produced multiple candidate high redshift galaxies whose inferred properties challenged expectations, though the field has also spent the past 2 years sorting robust cases from overestimates and photometric bias. That distinction matters. The scientific tension is real, but so is the caution. That caution is part of what makes this story credible. Weak science arrives drunk on certainty. Strong science arrives with friction. It argues with itself. It checks whether a bright object is truly distant or only dust obscured. It asks whether a stellar mass estimate assumed the wrong star formation history. It compares photometric redshifts with spectroscopic confirmation, because one is suggestive and the other is much harder to fake. Webb's most serious surprises are not the ones that looked impossible for a week. They are the ones that remain uncomfortable after the easy exits have been used up. And once you understand that, the emotional texture changes. This is no longer the thrill of scientists were wrong about everything. That line is cheap and almost always false. The deeper feeling is worse. Scientists may have been right about the framework and still wrong about the pace. Right about the ingredients and still wrong about the timeline. Right about the broad direction and still wrong about how quickly matter learned to organize itself into things that look, from a distance, disturbingly finished. Webb did not look back and find infancy. It found momentum already spent. That is the first fracture. Because the early universe was not supposed to be leisurely, but it was supposed to be constrained. There is a difference. No one imagined a quiet cosmic meadow slowly blooming in peace. The first generations of stars likely formed in violent bursts. Gas clouds collapsed under gravity. Radiation heated and disrupted nearby material. Mergers were frequent. Black holes began feeding. But even violence has a timetable. Chaos does not eliminate process. You still have to gather matter before you can compress it. You still have to cool gas before you can turn it efficiently into stars. You still have to build the invisible gravitational wells that galaxies fall into before a mature-looking galaxy can stand there shining into the dark. That invisible timetable is what makes the images dangerous. A galaxy is not only light, it is a record of assembly. When you see one in the early universe that appears surprisingly massive or chemically evolved, you're not simply seeing an object. You're seeing the amount of prior work reality must have done to produce it. Collapse, cooling, star formation, supernova feedback, enrichment, mergers, regulation, sometimes quenching. A bright early galaxy is not just a bright early galaxy, it is a compressed claim about everything that had to happen before the light left. And that is where the deeper unease begins to spread. Because if enough of those claims survive scrutiny, then the issue is no longer local. It is not about a single bizarre object. It is about whether the universe's first chapter was more efficient, more top-heavy, more accelerated, or more structurally prepared than we were comfortable assuming. Maybe baryons turned into stars with startling efficiency in certain halos. Maybe dust, feedback, and selection effects fooled some of us in one direction, and model prejudice fooled us in the other. Maybe dark matter scaffolding assembled regions of potential faster than the cleanest summaries suggested. Maybe something in the early conditions changed the tempo without overturning the underlying laws. None of these possibilities means cosmology is dead, but they all mean the old emotional picture of orderly emergence may have been too neat for the data now arriving. And this is why the story matters beyond astronomy. Human beings depend on intuitions about sequence. We trust maturation when it looks gradual. We trust complexity when it appears earned. The early universe comforted us because it seemed to obey that instinct at scale. First darkness, then sparks, then structure, then grandeur. Webb has not abolished that sequence, but it has begun to introduce an uglier possibility, that reality may reach complexity before our intuition is ready to call it plausible. That is the beginning of cosmological vertigo. Not that the universe is chaotic, not that science has failed, but that lawful things can still arrive sooner than the mind finds narratively acceptable. And once that possibility enters the room, the old timeline stops feeling like a neutral background. It becomes the thing under interrogation, because before we can decide whether Webb has truly found galaxies that do not belong where they are, we have to recover the deeper assumption hiding underneath the surprise. Why were we so sure the first universe would be slow enough to understand? Because too early only sounds dramatic until you see the machinery underneath it. From a distance, the old story of the early universe can seem almost decorative. A few textbook phrases, the cosmic dark ages, the first stars, Ryanization, the first galaxies. But those names were never just labels for eras. They were markers in a sequence of physical difficulty. Each one meant the universe had crossed a threshold it could not cross for free. That is why the standard picture felt so stable. It was not built on vague intuition, it was built on bottlenecks. The universe began hot enough that ordinary matter could not exist as neutral atoms. Electrons and nuclei moved through an opaque plasma, and light scattered constantly. There was no transparent sky yet, because there was no sky in the usual sense, no clear path for photons to travel untouched. Then, as expansion cooled everything, protons and electrons combined into neutral hydrogen, space became transparent enough for the relic glow of the cosmic microwave background to begin its long journey toward us. After that came a stretch often called the Dark Ages. No stars, no galaxies, no luminous structure yet, only matter, gravity, and tiny unevennesses waiting to grow. NASA's overview of the early universe describes the epoch of reionization as the period, ending when the universe was around 1 billion years old, in which radiation from the first massive stars reionized the mostly neutral hydrogen filling space. That sounds clean in summary. Lived as physics, it was slow violence. Imagine a universe filled mostly with hydrogen, cooling into darkness, with gravity trying to pull matter into denser pockets, while expansion keeps stretching everything apart. Nothing in that environment is allowed to skip process. Before you get a luminous galaxy, gas has to collect. Before it can form stars efficiently, it has to cool. Before those stars can alter their surroundings, Enough of them have to ignite to flood space with ultraviolet radiation. Before heavier elements can exist, stars have to live and die. Before a mature-looking system can appear in a telescope, a whole chain of invisible labour has to have already happened. That chain was the timetable, not because anyone wanted the first universe to be elegant, but because the universe itself seemed to impose speed limits. The earlier structures were expected to form inside dark matter halos, gravitational wells that gathered ordinary gas. In the standard model, small halos collapse first, then merge into larger ones. The visible galaxy is only the lit surface of a much deeper architecture. Long before starlight, gravity had to prepare the bowl. Only then could matter fall in hard enough, cool fast enough, and begin building something that could shine. Recent reviews of JWST's first billion-year observations still frame the field around exactly these questions. How early halos grew, how efficiently baryons turned into stars, how bursty those histories were, and how those processes fed rionization. This is where the emotional misunderstanding usually begins. People hear the early universe and imagine emptiness. But emptiness is the wrong instinct. The young cosmos was not empty. It was constrained. It was full of matter, radiation, and potential. But potential is not the same thing as realized structure. A mountain range inside the Earth's crust is not the same as a mountain already standing in the wind. What mattered was not whether the ingredients existed. What mattered was how fast they could organize into something legible. And legibility takes work. For hundreds of millions of years, the universe was trying to become visible to itself. That is what makes reionization such a profound part of the story. Once the first stars and galaxies formed in sufficient numbers, their radiation began tearing electrons back off neutral hydrogen, changing the state of the intergalactic medium. Space became transparent again, not because darkness vanished, but because luminous structure had finally become powerful enough to alter the medium around it. NASA and ESA both frame this era as one of the key reasons Webb exists at all. By seeing infrared-shifted light from extremely distant galaxies, it can probe how the first sources of light transformed the foggy early universe into a transparent one. That transformation already tells you something important. The first universe was not supposed to reveal itself all at once. It was supposed to emerge unevenly, locally, in islands, small bright regions in an ocean of neutral gas, patches of ionization spreading outward, bursts of star formation, feedback, collapse, disruption, enrichment, all of it jagged, all of it costly. Even the most dramatic early galaxies were still expected to be part of a broader story of gradual assembly across the first billion years. Webb has confirmed much of that complexity and exquisite detail, mapping early galaxies, their chemistry, their sizes, their star formation histories, and their role in reionization. But in doing so, it has also made one thing much harder to ignore. Some of those systems seem remarkably advanced for how little time had passed. And that is why the old timetable matters so much. Without it, surprisingly early means nothing. A galaxy does not become puzzling simply because it is distant. It becomes puzzling when its inferred properties imply too much prior history compressed into too little time, too much star formation, too much stellar mass, too much organization, too much chemical processing, sometimes, perhaps, too much black hole growth. The object itself is only the visible endpoint. The real question is what kind of early universe could have produced that endpoint quickly enough? This is the hidden pressure inside every Webb headline. Not, look how far away this is, but what had to happen before this light could exist? Once you ask that question, the young universe stops feeling like scenery and starts feeling like a budget. How much time for gas to fall? How much time for stars to ignite? How much time for supernovae to enrich their surroundings? How much time for halos to merge? How much time for a system to look not merely alive, but developed? That is why astronomers do not treat the first few 100 million years as a poetic frontier. They treat them like a narrow corridor. The corridor is physically rich, but not infinitely flexible. Push too much finished structure into it, and the model starts to strain. Which does not mean it breaks. That distinction matters. The public version of this story often swings between two bad extremes. Either nothing is wrong and every surprise will disappear, or everything is wrong and cosmology is collapsing. Neither is serious. The real scientific position is more demanding. Some early claims do weaken under better data. Some masses get revised downward. Some photometric redshifts turn out to be less secure than they first appeared. At the same time, the broader observational landscape really has changed. JWST has opened a detailed window onto the first billion years, and that window contains enough luminous, chemically interesting, and sometimes unexpectedly evolved systems that theorists are now forced to test whether the standard growth narrative needs adjustment in efficiency, timing, feedback, seeding, or something deeper. So the old picture was never wrong because it lacked grandeur. It may be wrong, where it is wrong, because it was too psychologically smooth. We like beginnings that look like beginnings. We like a young universe that behaves young. Small, dim, unfinished things feel narratively proper. They let us trust sequence. They let us believe that complexity arrives only after enough waiting. The standard model never promised that in a sentimental way. But our minds borrowed that feeling from it anyway. And now Webb has started to disturb that feeling. Because if the early universe was already capable of producing systems that seem older than their age should comfortably allow, then the first chapter of cosmic history was not just difficult, it was efficient in ways we do not yet fully understand. The darkness may not have been deep for long, and if that is true, then the next question is no longer about imagery. It is about one specific kind of object that turns early brightness into something far more dangerous. A galaxy that does not merely seem alive too soon, but seems to have already burned through a first life before the universe itself was even old enough to feel settled. And that is where the story stops being abstract. Because there is a difference between finding a galaxy that seems bright too soon and finding one that seems to have already finished a major chapter of its life. That is what makes GS 9209 so unsettling. At first glance, it is not the kind of object that would terrify a casual viewer. It does not need to. The real shock is hidden in what it is no longer doing. GS 9209 is a quiescent galaxy, a galaxy in which star formation has largely shut down. Not a system just beginning to blaze, not a raw nursery, not a brief flare caught in the act of assembly, a system that appears to have already undergone intense growth and then substantially stopped. JWST spectroscopy placed it at redshift 4.658, which means we're seeing it about 1.25 billion years after the Big Bang, and the analysis inferred a stellar mass of about 3.8 times 10 to the 10th solar masses. Even more striking, the team concluded that most of its stars formed in a relatively short burst, and that its star formation had already quenched when the universe was roughly 800 million years old. That is not just early. It is emotionally wrong. Because early galaxy still leaves room for youth. It still lets the mind picture something frantic, unfinished, half-built under difficult conditions. But a quiescent galaxy removes that comfort. It suggests not merely that structure formed fast, but that a large system may have already passed through an active life and entered a quieter state while the universe itself was still in what we instinctively want to call its youth. The University of Edinburgh summary of the result captured that tension plainly. This was an unusually early, already quiet, massive galaxy, with a stellar population comparable in scale to a far more mature-looking system than its cosmic age would seem to permit. It is one thing to find a city early. It is another to find ruins. That line is not literal, and the science should not be forced into poetry. GS 9209 is not a ruin drifting through space. It is a living galaxy, gravitationally intact, still physically present, still full of stars, but in evolutionary terms, it appears to have already come down from a period of ferocious construction. And that is exactly what makes it such a hard case. Brightness can be a flare, activity can be temporary, but a galaxy that seems to have formed a huge number of stars quickly and then largely stopped asks a much more dangerous question. What kind of early universe allows a system to reach that level of maturity? Then shut the door, all inside a window we once treated as barely enough time to begin. Notice how much hidden history is packed into that single object. To build that many stars, gas had to collapse efficiently into a dark matter halo. It had to cool. It had to ignite star formation at a remarkable rate. It had to enrich itself chemically through stellar evolution. And then something had to suppress or exhaust that growth quickly enough for the galaxy to appear quiescent by the time Webb caught its light. None of those steps is impossible on its own. That is why serious cosmologists do not call GS9209 a violation of physics. The problem is not permission, the problem is compression. Too much sequence appears to have been packed into too little time. And compression is where cosmological discomfort becomes real. The standard model does not fail because one galaxy is odd. A successful model can survive oddity. It can survive tales of distributions, rare environments, unusual merger histories, extreme feedback episodes. Nature always contains corners, but rare objects are still expensive. Every extreme case spends some of the model's flexibility. If the early universe starts producing too many systems that look prematurely massive, chemically evolved, or already quenched, then the issue stops being taste and becomes accounting. The recent Nature review on JWST's first billion years frames the field in exactly those terms. Not a cartoon collapse, but a mounting effort to explain early galaxies, early black holes, masses, morphologies, and star formation histories that are forcing theorists to revisit how efficiently structure emerged. This is why GS9209 matters even if it remains rare. It changes the emotional register of the evidence. Before objects like this, one could still imagine the early universe as mostly a contest between faintness and distance, a technical challenge. Build a better telescope, see the first lights, fill in the timeline. But a quiescent galaxy at this epoch turns the problem from visibility into biography. It is no longer enough to ask, how far away is it? Now you have to ask, what has it already been through? And once that question enters the frame, distance becomes secondary. The real subject is accumulated history. Webb did not merely find something ancient. It found something that already had a past. That distinction is devastating, because the first billion years was supposed to be a time when the universe was still improvising. Dark matter gathering, gas falling, star formation switching on in jagged bursts, reionization unfolding in patches. The cosmos was not yet expected to be full of systems that feel post-burst, post-peak, almost post-youth. A galaxy like GS9209 suggests that in at least some places, the universe moved from emergence to maturity with a speed that makes our mental picture of cosmic beginnings feel narratively naive. But honesty matters here. No single object can carry the weight of a revolution. It would be irresponsible to turn GS9209 into proof that cosmology is broken. Even its interpretation depends on population synthesis models, assumptions about star formation histories, and the difficult translation from spectra into evolutionary story. The right response to a case like this is not surrender to hype. It is pressure with discipline. How secure is the redshift? In this case, secure enough to matter. How robust is the quiescent interpretation? Strong enough to unsettle the field? How representative is it? That remains an active question, and the answer matters enormously. Still, even with all that caution left intact, the object does something irreversible. It widens the imagination of what the young universe may have been capable of. Once a galaxy like this exists in the observational record, theorists do not just have to explain it, they have to explain the path to it. Was star formation in some early halos far more efficient than expected? Were mergers rapidly assembling mass in ways simulations undercounted? Did black hole feedback help quench some systems astonishingly early? Are our assumptions about the stellar populations of these galaxies skewing the inferred masses and ages? Or are we touching a deeper issue? Not broken laws, but incomplete opening conditions. That is the real movement of the story. A bright object becomes a mature object. A mature object becomes a compressed history. A compressed history becomes a problem for the timeline. And once the timeline itself is under pressure, one galaxy is no longer enough. Because the next question is the one successful theories fear most. Not, can I explain this one? But how many of these can I afford? That is the question a healthy theory can sometimes answer. The more dangerous question is whether it can answer it repeatedly. One extreme object is a test of flexibility. A whole population of them becomes a test of architecture. This is where the tone of the story changes again, because science can absorb surprise more easily than abundance. A theory is allowed a monster. It is not so easily allowed a census. Once Webb began returning large samples of very distant galaxies, astronomers were no longer dealing only with dramatic individual cases. They were dealing with number density. how many luminous or apparently massive systems seem to exist at a given epoch, and what that count implies about how quickly matter was assembling into visible structure. Recent reviews of Webb's first billion-year results describe exactly this shift. The field has moved from isolated detections to the much harsher work of building a census of early galaxies, their luminosities, masses, morphologies, and star formation histories. And a census is merciless, because a single galaxy can be explained with luck, a population cannot. If enough systems appear brighter than expected, then perhaps star formation was more efficient than the models assumed. If enough systems appear more massive than expected, then perhaps the conversion from light to stellar mass has been biased. If enough systems look chemically mature, compact, structured, or already on their way toward quiescence, then the hidden timetable under the first billion years starts to feel compressed not in one place, but everywhere you look. That is why the debate around early Webb galaxies has been so intense. It is not really a debate about whether one object is weird. It is a debate about whether the emerging distribution of objects can still be generated naturally inside the old growth narrative. This is also where the science becomes more honest and more interesting than the headlines. Some of the earliest claims of impossibly massive galaxies were too strong. Better infrared coverage from Webb's MIRI instrument has already revised parts of that picture downward. One recent analysis found that excluding MIRI data tends to overestimate stellar masses for massive galaxies at high redshift, and when those longer wavelength constraints are included, the inferred number densities of the most massive early galaxies drop substantially, by about 36% for galaxies above 10 to the 10th solar masses, and about 55% for those above roughly 10 to the 10th.3 solar masses in the redshift range they studied. That matters, because it means some of the loudest early panic was partly a measurement problem. But that does not return us to comfort. It only removes the weakest version of the crisis. Even after those revisions, the broader observational pressure remains real enough that the community is still treating the early abundance problem as an open question, rather than a solved embarrassment. The major reviews published after Webb's first 2 years do not describe a collapse of cosmology, but they do describe a transformed landscape in which the census of early luminous and massive galaxies has become a central test for galaxy formation models. That is a much more unsettling position than either triumph or panic, because now the argument moves into a narrow corridor where every explanation costs something. If you lower the inferred stellar masses, you relieve some pressure, but not necessarily all of it. If you assume extremely bursty star formation histories, you can make some galaxies appear less impossibly mature, but then you have to explain how such bursts became so efficient so early. If you lean on dust corrections, feedback physics, selection effects, or active galactic nuclei contaminating the light, each of those helps in some cases, but each also shifts the burden elsewhere. The theory survives by spending flexibility, and once you notice that, abundance becomes the true antagonist of this story. Because abundance is what turns anomaly into atmosphere. A single surprising galaxy still allows the old universe to feel intact. A visible pattern of them changes the weather. That is why cosmologists care so much about luminosity functions and stellar mass functions. These are not bureaucratic charts. They are the emotional accounting sheets of the universe. They tell you how common different kinds of systems were at different times, and whether the pace of emergence was modest, violent, or disturbingly efficient. If the high redshift luminosity function turns out to be richer than expected at the bright end, that is not just a counting discrepancy. It suggests that early star formation may have become organized into visible, powerful structures faster than the smoothest versions of the standard story led us to expect. And notice what has happened to the tension by this point. We are no longer talking about images. We are no longer even talking mainly about galaxies. We are talking about budgets. How many halos had to be ready? How many baryons had to cool? How many stars had to ignite? How much enrichment had to occur? How often could this happen before surprising stopped being the right word? That is why abundance is more dangerous than spectacle. Spectacle can be rare. Budgets have to close. And the early universe did not give us much room to hide. These galaxies are being seen in epochs when the cosmos was still passing through rionization, or emerging from it, when neutral hydrogen still mattered, when structure was supposed to be building unevenly out of a much simpler background. The first billion years were already a narrow corridor. a richer than expected population of bright or massive galaxies narrows it further. The old comfort then was never just that one could explain the first galaxies. It was that one could explain them statistically. Webb has not taken that confidence away completely, but it has made it conditional. Now the field has to ask not merely whether an individual case can be rescued, but whether the ensemble can still be made to look natural. And that question is harsher, because it reaches beneath the visible galaxies into the invisible architecture that had to come first. Before starlight became puzzling, gravity had to make it possible. Before a galaxy could look too old, something had to prepare the bowl it formed inside. Which means the next step down is unavoidable. If too many visible systems seem ahead of schedule, then perhaps the real issue is not the stars we see, but the hidden scaffolding that may have been forming too fast in the dark. Because the stars are only the visible confession. The real work begins long before anything shines. Every galaxy Webb sees is sitting inside something darker, older, and far less forgiving than starlight suggests. A halo of dark matter. Not dark in the poetic sense. Dark because it does not emit light, does not absorb it in any ordinary way, does not reveal itself except through gravity. And yet this invisible material is the first architecture that matters. Before gas can gather, before stars can ignite, before a galaxy can look startlingly mature, gravity has to dig the well. That well is the halo. You can think of a galaxy as the bright weather inside an invisible landscape. The stars are not the ground. They are what happens when ordinary matter falls into terrain carved by something deeper. In the standard picture, dark matter begins this work early, amplifying tiny primordial density differences into growing structures. Small halos collapse first, they merge, accrete, and deepen. Ordinary gas falls into them, gets compressed, cools if it can, and only then turns into stars. Recent reviews of JWST's first billion-year results still frame early galaxy formation through exactly this hidden sequence. Halo growth first, then baryon accretion, then the uncertain efficiency with which gas becomes starlight. That is why the abundance of bright early galaxies is so unsettling. It is not merely telling us that stars formed early. It is telling us that the invisible scaffolding beneath them may have been ready early enough, massive enough, and efficient enough to host that light. And that is not a trivial revision. Because once you descend from galaxies to halos, the room for storytelling gets smaller. Visible light can deceive, stellar population models can shift, dust can make a galaxy look older, redder, or more massive than it really is. Active black holes can contaminate what seems like pure starlight, but the halo question is more severe. However we revise the visible interpretation, there still has to be enough gravitational preparation underneath the object to make the object plausible at all. Before you can build a galaxy, the universe has to prepare the gravity. That line is the spine of this whole problem. A luminous early galaxy is not just a bright event. It is a statement about how quickly matter found depth, how quickly small primordial irregularities became gravitational basins strong enough to trap gas, compress it, and hold on to enough of it to produce real structure. If too many galaxies appear unusually early and unusually developed, then one possible answer is that the baryons, the ordinary matter, were simply far more efficient at turning themselves into stars than we are used to assuming. Another is that the halo population at those redshifts, especially at the massive end, functioned in a way our cleanest summaries have not captured well enough. This is where the debate becomes both more technical and more philosophically sharp. Because the standard cosmological model does not just predict that halos exist, it predicts how structure should grow statistically from the initial conditions imprinted in the early universe. Change the abundance of early halos, or change the efficiency with which those halos convert gas into stars, and you can make the visible universe look dramatically different without rewriting gravity from scratch. That is one reason many researchers have focused first on astrophysical explanations rather than immediate claims of new fundamental physics. The 2024 Macross study is a good example of this restraint. After including MIRI data, it reduced the inferred abundance of the most massive early galaxies, but it still found that matching the remaining population within standard cosmology required a moderate increase in baryon to star conversion efficiency at high redshift, with values around 0. 3 for the most massive systems at Z around 8, compared with much lower typical efficiencies in the nearby universe. That may sound like a dry parameter adjustment. It is not. It means the early universe may have been startlingly good at building visible structure once the right halos existed. In other words, the dark scaffolding may not need to be radically different for the visible outcome to feel radically different. Perhaps the main revision is not that halos formed impossibly early, but that the gas inside some early halos cooled fast, collapsed hard, and resisted stellar feedback more effectively than our later universe intuition prepared us to expect. Dense gas has short freefall times. In extremely compact, gas-rich environments, star formation can proceed with a brutality that makes low redshift comparison misleading. The same Macross work points towards suppressed stellar feedback in high-density early halos as one plausible route to producing these galaxies without abandoning lambda CDM outright. That possibility is scientifically conservative. It is also emotionally destabilizing, because it means the early universe may not need exotic laws to outrun our intuition. It may only need familiar laws operating under less familiar conditions, with greater efficiency, higher densities, and less wasted motion than we expected. The humiliation is subtler then, not that physics failed, that we made the opening chapter feel too slow because we had quietly imported the pacing of the later universe into a period that may have been much more savage. The first universe was not gentle. It may also not have been patient. Still, the halo question does not let us off easily. Even if you increase star formation efficiency, the deepest visible systems still require substantial underlying structure. A galaxy that looks massive at very high redshift still implies a halo history behind it. Assembly, mergers, accretion, potential wells deep enough to hold gas against disruption. And as researchers keep building larger samples, the tension moves back and forth between two linked unknowns. Are we underestimating how fast halos of the relevant mass assembled, or are we underestimating how violently ordinary matter exploited those halos once they appeared? The honest answer, at the moment, is that both remain in play. That uncertainty is not weakness, it is the real drama. Because this is what a scientific pressure point actually looks like when it is alive. Not a model shattering in public, a model being forced into precision. Every new Webb galaxy asks the same question in a more demanding tone. Where, exactly, is the bottleneck? In halo growth? In gas cooling? In feedback? In the mapping from light to mass? In the initial conditions? In some missing ingredient that only becomes visible this far back? And once you start asking that question seriously, the early universe stops feeling like an image and starts feeling like an efficiency machine. A machine that may have wasted less time than we thought. Which is why the hidden scaffolding matters so much. Because if the dark structure underneath these galaxies was ready unusually early, or if the first halos became astonishingly efficient furnaces for star formation, then the visible surprises Webb is finding are not independent curiosities. They are symptoms of one deeper fact. The young universe may have organized itself faster than our story allowed. And once that possibility becomes real, another crack in cosmology stops looking like a separate problem entirely. Because while Webb was forcing us to ask whether the first structures formed too quickly, a different set of measurements had already been asking something just as corrosive. Not how fast galaxies grew, how fast the universe itself is expanding, because timing was already under suspicion before Webb ever sent back its first impossible-looking dawns. A separate crack had been widening for years, and it lived in a different part of cosmology's confidence, not in the growth of galaxies, but in the expansion of space itself. The question sounds simple enough to fit on a page. How fast is the universe expanding right now? But that single number, the Hubble constant, is not just a rate, it is a hinge. It connects distance to recession, present expansion to cosmic age, nearby measurements to the deep early universe. NASA describes it as a value that helps unlock fundamental questions about the speed of expansion and the age of the cosmos. And for a long time, the expectation was not that every method would be identical in practice, but that after enough refinement they would converge on the same underlying reality. Instead, they did something worse than disagreeing noisily. They disagreed cleanly. One route starts with the early universe, the cosmic microwave background, observed in exquisite detail, then interpreted through the standard cosmological model to infer what the present expansion rate should be. Another route stays close to home, build a distance ladder from Cepheid variable stars, calibrate Type 1, a supernovae, and measure the expansion more directly in the nearby universe. These two approaches have persisted in giving different answers, and the gap has become known as the Hubble tension. NASA's recent explainer and mission reporting frame this as a genuine unresolved puzzle, rather than a trivial calibration mismatch. That phrase, Hubble tension, can sound oddly soft for what it implies. A tension in cosmology is not a mood. It is a situation where two precision routes to reality refuse to reconcile under the same model. And this is what made the problem so corrosive. The standard model was not failing in a dramatic cloud of contradiction. It was failing, if failing is the right word, in a highly disciplined way. The numbers were too good to dismiss, too stable to laugh off, and too consequential to keep quarantined as a technical nuisance. NASA's 2024 coverage emphasizes exactly that point. After nearly 3 decades of refining the local distance ladder, the disagreement remains, with the lower early universe value and the higher local value still not naturally settling onto one answer. And that is where Webb entered a story that was already raw. One conservative hope had always been that the local side of the tension, the side using Cepheids and supernovae, might still contain subtle measurement errors. Hubble, magnificent as it is, works in optical and near-infrared bands where crowding and blending can matter. In distant galaxies, nearby stars can contaminate the apparent brightness of Cepheids, and if those milepost markers are even slightly mismeasured, the whole ladder can tilt. Webb was powerful here not because it could invent a new universe, but because its sharper infrared vision could revisit those Cepheids with less contamination and test whether the nearby route discrepancy was partly an observational illusion. NASA reported the outcome in unusually direct language. Webb and Hubble together strengthen the case that the tension persists and is not simply an error in Hubble's measurements of crowded Cepheid fields. That matters more than almost any headline ever captured. Because a puzzle is one thing. A puzzle that survives a better instrument becomes a pressure point. Webb did not solve the Hubble tension. It made the easy escape route narrower. By checking Cepheids in the galaxies that anchor the supernova distance scale, it helped show that the local measurement was not just a blurry mistake made by an older telescope. NASA's summary put it plainly, with measurement errors increasingly negated. The remaining possibility is that something in our cosmological understanding may be incomplete. This is the moment the emotional geometry changes. Until now, the early galaxy story could still be contained as an astrophysical discomfort. Maybe the first halos were unusually efficient. Maybe star formation was burstier. Maybe dust, feedback, and mass estimates were hiding the simpler explanation under a layer of misread light. All of those remain possible in individual cases, but the Hubble tension lives at a different level. It is not mainly about how galaxies behave inside the model. It is about whether the model itself is translating the universe's history into a single coherent present. The universe is not only growing, it is disagreeing about how fast. That line is where the two crises begin to lean toward each other. Not because they are already proven to have one common cause, that would be stronger than the evidence allows. It is important to say this cleanly. There is no scientific consensus that Webb's early galaxy tensions and the Hubble tension are the same problem. They may yet end up partly separate, partly overlapping, or mostly resolved through different revisions. But the overlap is no longer speculative nonsense either. It has become serious enough that researchers are openly testing models designed to ease the Hubble tension, especially early dark energy scenarios, against the abundance of bright early galaxies Webb is finding. One 2024 study found that an early dark energy cosmology could ease both the Hubble tension and some of the apparent high redshift galaxy abundance puzzles more naturally than baseline lambda CDM under the same empirical galaxy formation framework, particularly at the highest redshifts. That does not mean early dark energy is the answer. It means the wall between expansion problem and early structure problem has started to thin. And once that happens, cosmology begins to feel less like a set of separate anomalies and more like a model under cross-examination from multiple directions at once. On one side, Webb is showing us galaxies whose development can look uncomfortably accelerated. On the other, improved measurements of the local universe continue to resist the expansion rate inferred from the early one. Neither issue alone forces a revolution. Together, they produce a different emotional pressure. The sense that our summary of the opening universe may be too tidy to survive contact with new data forever. And this is where one has to resist the temptation to become cheap. It would be easy to say the universe is broken, easy to say everything we knew was wrong, easy to turn statistical disagreement into metaphysical collapse. But reality is usually more demanding than that. The standard model of cosmology still explains an enormous amount with extraordinary success. It remains one of the most powerful syntheses in science. What Webb and the Hubble tension are doing is not erasing that success. They're exposing where success may have hidden unresolved strain, which is, in a way, even more unsettling. Because a failed model can be discarded, a successful model with cracks has to be lived with. It has to be tightened, pressured, extended, perhaps amended in one place and defended in another. That is the atmosphere cosmology is entering now. Not collapse, but discomfort with memory. The equations still work astonishingly well, and yet the universe keeps returning results that feel as though they were produced by a slightly different opening chapter than the one we learned to trust. And once you feel that, the story stops being about data points and starts becoming about chronology itself. Maybe the early universe built structure faster than expected. Maybe the expansion history contains a missing ingredient. Maybe both tensions are shadows cast by some deeper mismatch between the universe we infer backward and the universe that actually unfolded forward. That is the renewal point. Because the real question is no longer whether Webb found a few galaxies that look too old. The real question is what kind of cosmos produces both accelerated-looking structure and a stubborn disagreement about its own expansion history, and why the strain seems to grow precisely when we look closest to the beginning, which is when the question gets bigger than galaxies. Up to this point, the pressure could still be described in local terms. A few objects form too quickly, a few systems seem too bright, too massive, too chemically evolved, too far along in their own internal histories. Even the Hubble tension, for all its reach, could still be spoken of as a disagreement over one parameter. Important, yes. Deeply inconvenient, yes, but still contained inside the language of measurement. That containment does not survive the midpoint. Because once early structure and cosmic expansion both begin to look slightly ahead of schedule, the problem is no longer just what Webb found. The problem is the bridge that was supposed to connect the first universe to the present one. Webb's observations have transformed the empirical picture of the first billion years, while the Hubble tension result remains a live disagreement between early universe inference and late universe measurement, taken together. They do not yet prove one common failure point, but they do force the same unsettling question. Is the timeline we use to narrate cosmic history too smooth to carry all the data now arriving? That is a much harsher kind of doubt than maybe some galaxies are weird. It means the model may still be broadly right and yet wrong in exactly the place that matters most, in how it turns the young universe into the older one. A cosmological model is not just a box of ingredients, it is a translation engine. It takes tiny primordial fluctuations, invisible matter, radiation, expansion, gravity, time, and converts them into a universe with structure, chemistry, stars, black holes, galaxies, clusters, and finally us. When that engine starts producing results that feel just slightly mistimed in more than one place, unease spreads upward. The issue stops being any one discovery. It becomes chronology itself. This is the moment Webb's role becomes stranger than powerful telescope. Because Webb was never supposed to merely collect prettier evidence. It was supposed to sharpen a successful story, look farther back, reduce uncertainty, fill in the early chapters, and make the opening universe feel more continuous with everything that came after. In one sense, it has done that beautifully. It has revealed early galaxies in extraordinary detail, pushing the census of very high redshift systems and clarifying their luminosities, sizes, morphologies, ionizing output, and star formation behavior. But in another sense, that same success has made the universe less narratively obedient. The sharper the picture becomes, the harder it is to keep pretending the remaining strain is just noise around the edges. The telescope did not just find strange things, it found leverage. That is why the emotional temperature changes here. Before this point, the viewer can still imagine that each anomaly belongs to its own compartment. Early bright galaxies over here, a stubborn expansion rate disagreement over there, maybe some black hole puzzle in another corner. But science does not experience pressure that way for long. Once multiple tensions begin to gather around the same era, the opening stretch of cosmic history, the walls between them start to feel provisional, not because we have already unified them, we have not, but because the possibility that they are symptoms of one deeper misdescription becomes too serious to dismiss as literary overreach. And that possibility is precisely what makes this the real midpoint of the story. Not the universe is broken, not everything we knew was false, something more difficult. The universe may have been lawful all along, while our summary of its opening chapters was too psychologically tidy. That is a more mature form of fear, because it does not offer the relief of total collapse. Total collapse is clean. You throw out the old map and begin again. What Webb is doing instead is forcing cosmology into an uglier experience, living with a map that still works astonishingly well, while more and more of the terrain starts to feel as though it was drawn by someone who had not yet travelled far enough into the dawn. NASA's own framing of the Hubble result captures that tone unusually well. Not a discarded universe, but the real possibility that something in our understanding remains incomplete after measurement errors are squeezed away. And once incompleteness becomes the true subject, the scale changes. The early galaxies stop being the story. The Hubble constant stops being the story. Even Webb itself stops being the story. The story becomes the hidden continuity we thought we had. A cosmology is only as strong as the path it draws from beginning to now. If that path needs unusual efficiencies, special pleading, or repeated local adjustments every time we interrogate the first billion years a little more deeply, then the tension is no longer observational. It becomes philosophical in the most disciplined scientific sense of that word. Not philosophy as decoration. Philosophy as the architecture of explanation. What counts as natural growth? What counts as an acceptable amount of tuning? At what point does a model stop predicting a universe and start chasing one? That last question is brutal because cosmology has earned our trust. Lambda CDM is not a flimsy story waiting to be mocked. It is one of the great syntheses in science. It explains the large-scale distribution of matter, the relic background of the early universe, structure growth, and much else with astonishing reach. That is exactly why the present discomfort feels so serious. Weak models can be ignored. Strong models are wounded slowly. The first billion years, according to Webb, are now rich enough, varied enough, and demanding enough that the old comfort of the details will settle no longer feels sufficient by itself. And now, for the first time, the radical thought becomes responsible. Not that gravity is false, not that the Big Bang did not happen, not that cosmology has been humiliated. Only this. The opening universe may have carried an extra ingredient, an altered pacing, or a hidden pressure term that made early structure and later expansion look the way they do. That is why ideas like early dark energy have become so compelling to some researchers. They are not attractive because they are sensational. They are attractive because they offer the rare thing every scientific crisis wants, a way to let two discomforts talk to each other without dissolving rigor. The 2024 Early Dark Energy study explicitly explored whether a model introduced to ease the Hubble tension could also make Webb's bright early galaxies less strained, and found that it could relieve both pressures more naturally than baseline lambda CDM in some of the highest redshift regimes they tested. That is not proof, but it is enough to turn a speculative bridge into a serious one, which means the question has now crossed a threshold. It is no longer, why does this galaxy look too old? It is, what kind of universe produces a whole opening chapter that seems slightly too advanced for the pace we thought we understood? That is the second ignition, because once that question becomes legitimate, the next descent has to leave visible objects almost entirely and move into older, colder evidence. Evidence that was already sitting in the background before Webb ever launched, waiting to be reinterpreted under a harsher light. Ancient light, old anomalies and new pressure. And suddenly the microwave afterglow of the Big Bang stops looking like settled history and starts feeling like testimony. Because the oldest evidence in cosmology never stopped speaking. We just got used to hearing it as confirmation. Long before Webb began pulling impossible-looking structure out of the dark, the cosmic microwave background had already given us the deepest observational portrait of the young universe ever made. It is the relic light from when the cosmos cooled enough for neutral atoms to form and photons could finally travel freely. And Planck's measurements turned that afterglow into one of the great triumphs of modern science. ESA and the Planck collaboration still describe the 6-parameter lambda-CDM model as an excellent fit to the CMB data, and Planck remains the strongest single source of constraints on that standard picture. That success is exactly what makes the remaining discomfort so strange. Because the microwave background did not only give cosmology precision, it also left behind a residue of low-level unease on the larger scales. Not a decisive contradiction, not a clean falsification, something harder to metabolize, a pattern of large-angle oddities that never became strong enough to overthrow the model, yet never fully disappeared either. Planck's 2018 isotropy and statistics analysis says this plainly. The data are broadly consistent with Gaussian lambda-CDM expectations overall, but they also confirm the presence of several so-called anomalies on large angular scales. ESA's public summary says much the same thing in simpler language, noting that the larger scale temperature fluctuations are weaker than expected, and highlighting asymmetry and the cold spot among the features that drew attention. For years, those anomalies lived in an awkward category, too well known to ignore, too statistically delicate to canonize, too suggestive to forget. That awkwardness matters. A mature science learns to live with blemishes. It does not panic every time the sky looks slightly less random than expected. Large-angle anomalies in the CMB have always been haunted by a hard question. Are they evidence of something deep, or are they simply what chance looks like when human beings stare too long at one sky? Planck never endorsed a dramatic answer. Its position was more disciplined. The standard model still fits astonishingly well, but features such as low large-angle correlation, hemispherical asymmetry, and certain alignments remain unusual enough to be discussed rather than erased. And when the rest of cosmology felt stable, that restraint was enough. The anomalies could remain background discomfort, a footnote to success, a reminder that one observed universe can always contain statistically awkward patterns without demanding new laws, but pressure changes the meaning of old evidence. Once Webb begins showing an early universe that may have formed luminous structure faster than expected, and once the Hubble tension continues surviving improved scrutiny, the emotional status of those CMB blemishes changes. They do not suddenly become proof of new physics. That would be irresponsible. But they do become harder to wave away with the old confidence that every discomfort is safely isolated. Noise becomes harder to dismiss when the rest of the universe has started misbehaving. Take the large-angle sky itself. Planck's newer visual material still emphasizes that, when filtered to scales of around 5 degrees and larger, the CMB carries broad temperature structure across the whole sky, rather than a featureless statistical wash. That alone is not surprising. The anisotropies are real and expected. The discomfort comes from how some of those larger scale patterns compare with the cleanest isotropic expectations. ESA's summaries point to weaker than expected large-angle fluctuations and hemispherical asymmetry, while later reanalyses continue to revisit whether these effects persist in updated map treatments such as PR4. Recent papers have found that several of the large-angle anomalies remain at similar qualitative levels in newer data products, even when specific secondary explanations from the local universe appear too small to erase them. That is not a revolution. It is something scientifically colder. It means the anomalies have survived long enough to remain annoying, while staying weak enough that no responsible cosmologist can build a whole new universe on them alone. This is why the language around them has stayed so careful. Planck's own statistical analysis does not present them as decisive evidence against lambda-CDM. It presents a model that works extremely well overall, alongside a handful of large-angle features that are persistently unusual. The field's more recent re-examinations keep doing the same thing, refining, testing, downgrading some proposed explanations, and asking whether anything genuinely physical sits underneath the discomfort. And that careful language is the very reason they belong in this story. Because premium tension in science is not created when the evidence is loud. It is created when the evidence is quiet but recurring. A single dramatic contradiction can be dismissed as error. A collection of small, stubborn irregularities is harder. They do not give you the relief of certainty in either direction. They just sit there, changing the psychological background of a field. That is what the CMB anomalies have done. They have not overthrown the standard model. They have made the standard model feel ever so slightly less complete at the largest observable scales, especially once other early universe tensions enter the room. Ancient light, then, is no longer merely a monument to cosmological success. It is also a reminder of how success can conceal unresolved strain. That is the real shift happening here. Before Webb, the microwave background could be treated as the settled opening statement, with everything else following downstream. Now the flow feels less one way. Webb's early galaxies do not rewrite Planck. Planck's anomalies do not explain Webb, but together they create a harsher interpretive atmosphere. The first universe may have been statistically lawful, and still less psychologically simple than our best summary of it. And once that atmosphere exists, another threshold is crossed. Because the question is no longer only whether the young universe looked odd in one relic map, or whether a few early galaxies appear too mature. The question becomes whether the first cosmos was organizing itself with a speed and readiness that left traces at multiple levels, in the background light, in the growth of visible structure, and perhaps in the environments where whole systems were already beginning to gather. Not just galaxies, arrangements of galaxies, not just isolated brightness, a broader pattern of readiness. And that is where the pressure deepens again, because once you stop looking for solitary anomalies and start looking for early organization itself, the universe begins to feel less like a place that slowly woke up, and more like a place that may have become structured before our intuition would have allowed. Because once early organization becomes visible, the emotional texture changes again. A strange galaxy can still be treated as an outlier. Even a small class of them can sometimes be absorbed as a revision to star formation efficiency, dust modeling, or halo growth. But when multiple galaxies appear not merely early, but early together, occupying the same dense environments, tracing over densities, beginning to resemble the seeds of larger cosmic structures, the universe stops looking lucky and starts looking prepared. Recent JWST work has begun identifying protocluster candidates and dense overdense regions at redshifts above 4.5 and even above 7, which is exactly the regime where structure was supposed to be emerging, not already learning to gather into environments with recognizable collective behavior. That distinction matters more than it first appears, because a galaxy is one timeline. An environment is many timelines that have already begun to converge. A protocluster is not yet the kind of fully mature galaxy cluster we see nearby, with its giant central galaxy, hot intracluster gas, and long-settled hierarchy. It is the earlier, more violent version, an overdense region destined, in some cases, to become one of those massive structures later on. But even in that unfinished state, a protocluster means something severe. It means the universe is not only forming objects, it is already arranging neighborhoods. The review literature on JWST's first billion years emphasizes this widening scope clearly, moving from individual galaxies to their environments, clustering, and the emergence of a large-scale structure as part of the new observational frontier. This is where the phrase "the early universe" quietly fails us. It makes that era sound uniform, as though the cosmos was simply young everywhere in the same way. But real structure formation was never evenly distributed. Density fluctuations meant some regions were always ahead of others. Gravity gives advantage to the slightly denser patch. It deepens a lead. It makes the rich region richer. So in one sense, early overdensities are not surprising at all. They are expected. The issue is not whether they exist. The issue is how pronounced, how common, and how quickly they start looking like the embryos of later cosmic architecture. Surveys using JWST across CEERS, JADES, and PEARLS fields have already identified thousands of robust high redshift galaxy candidates and used them to search for protocluster candidates between redshifts 4.5 and 10, explicitly treating environment as a major part of the story rather than a side note. That is the deeper escalation. The surprise was no longer a galaxy, it was a pattern of readiness. Once you see multiple young systems crowding together in a tiny region of space, all participating in a denser-than-expected local structure, the imagination changes scale. We are no longer looking at a few bright islands in darkness. We are looking at the possibility that some parts of the cosmos were already becoming socially gravitational, already building the conditions under which mergers, feedback, black hole growth, chemical enrichment, and accelerated star formation could reinforce each other. In recent JWST/NIR spec work on protocluster environments above redshift 7, researchers found not only dense environments but systematic differences in member galaxies, including higher ionizing photon production efficiency and signs of intense star formation compared with field galaxies, even while the surrounding gas could remain substantially neutral. That last detail is especially haunting, because it means early organization does not arrive into a calm, transparent universe. It emerges inside a medium that is still partly opaque, still undergoing rionization, still unfinished on the largest radiative scales. So now the image is harsher, luminous systems clustering inside regions where the surrounding hydrogen has not yet fully yielded, pockets of concentrated activity embedded in a cosmos that is still, in a profound sense, incompletely awake. The same 2025 protocluster environment study argues that rionization remained highly patchy and strongly modulated by environment, with local overdensities boosting the ultraviolet output while not necessarily clearing their surroundings completely. This is no longer just early galaxies formed faster than expected. It is, some parts of the universe may have begun behaving like ecosystems before the global background had caught up. That is a very different feeling. Because ecosystems generate momentum, a dense region is not simply many galaxies placed side by side. It is a feedback amplifier, more interactions, more mergers, more opportunities for gas inflow, disruption, quenching, black hole feeding, and rapid restructuring. Once the universe begins producing such environments early enough, the apparent maturity of some individual galaxies becomes easier to imagine. But the price is that the universe as a whole begins to look more aggressively self-organizing than the cleanest versions of the old narrative implied. The 2025 Nature Review on the first billion years according to JWST treats this exact widening as part of the field's transformation, highlighting environments, overdensities, early black holes, galaxy assembly, and the broader emergence of structure rather than isolating each into separate stories. And then there are the cases that make the word protocluster feel almost too gentle. In 2026, researchers reported a combined JWST and Chandra detection of JADES-ID1, a protocluster at redshift about 5.68, roughly 1 billion years after the Big Bang, with X-ray emitting hot gas and an inferred gravitating mass on the order of 10 to the 13th power solar masses, positioning it as a progenitor of today's most massive galaxy clusters. That does not mean mature clusters were common that early, or that all formation models are broken, but it does mean the universe was capable, at least in some places, of reaching surprisingly advanced stages of collective gravitational organization very early in its history. That kind of result changes the rhythm of the whole script. Because now, too early, is not just about stars or galaxies, or even black holes in isolation. It is about structure on multiple levels beginning to line up: visible light, dense environments, massive precursors to later clusters. The universe starts to feel less like a stage on which isolated marvels briefly appear, and more like a system that may have been assembling hierarchy with unnerving efficiency from the beginning. And once hierarchy appears early, every other tension becomes heavier. Bright galaxies are no longer lonely miracles. They may be the local surface of a deeper organizational speed. Still, discipline matters here. None of this justifies saying that large-scale structure should not exist so early. That would oversell the case. Protocluster candidates are difficult to confirm, selection effects matter, and overdensities can sometimes be interpreted differently depending on survey geometry, spectroscopy, and halo mass inference. Even the Vatican Observatory Conference note on early large-scale structures makes this caution visible, pointing out that an overdensity may signal a larger structure or a smaller protogroup, and that wider characterization is needed before halo mass and evolutionary destiny are pinned down securely. But caution does not erase the shift in atmosphere. It sharpens it. Because the careful version is already enough. The first universe may not only have formed luminous objects quickly, it may also have begun assembling contexts quickly, the kinds of dense, interactive settings that accelerate history. That means the early cosmos was not just producing surprises, it was building the conditions for more surprises to become likely. The young universe may not have been merely bright ahead of schedule. It may have been organized ahead of schedule, and once that thought becomes plausible, another pressure point starts to darken at the center of the field. Because nothing embodies accelerated cosmic advantage more brutally than an object that seems to begin life already ahead, a supermassive black hole in the first universe, growing fast enough to make even these overdense environments feel like preparation rather than explanation. And this is where the early universe becomes almost offensive to human intuition. Because galaxies forming too fast is one thing, dense environments appearing early is another, but a supermassive black hole in the first universe carries a different kind of insult. It does not merely suggest that structure formed quickly, it suggests that in some places, gravity found a way to concentrate power so efficiently that the rest of the timeline starts to look slow by comparison. A black hole is already a difficult object to narrate honestly. Popular language makes it sound like a cosmic vacuum cleaner or an exotic monster. But in this story, the important fact is simpler and harsher. Black holes are clocks on growth. If you find one with millions or billions of solar masses when the universe is still very young, you are forced to ask how it got there in time. Not in myth, in sequence, seed mass, accretion, mergers, feedback, radiation pressure, duty cycle. Every one of those terms is really the same question in different clothing. How did it get so large so fast? That question has been sitting at the centre of early black hole physics for years, but JWST has changed its scale. A recent review of the first billion years, according to JWST, explicitly treats early massive black holes as one of the field's major pressure points. Not because the existence of early accreting black holes was unknown before Webb, but because the new census is getting richer, stranger, and harder to keep psychologically separate from the rest of the early structure problem. Some objects are already startling enough on their own. ESA reported a JWST confirmation of an actively growing supermassive black hole only about 570 million years after the Big Bang. That kind of system does not merely light up the early universe. It announces that a central engine with enormous appetite was already in place when cosmic history was still supposed to be in its opening movements. And then there is the broader population effect. JWST has been uncovering what appear to be surprisingly numerous active galactic nuclei in the first billion years. Black holes in the rough range of millions to hundreds of millions of solar masses, caught while feeding inside young galaxies. A 2024 MNRAS paper described this directly as a surprising finding, emphasizing the growing number of AGN associated with moderately massive black holes at redshifts above 5. This is where the tension becomes more severe than with galaxies alone. A galaxy can look mature because our assumptions about its stellar populations were off. Its inferred mass can come down. Its star formation history can be reinterpreted. Dust can mislead. But black hole growth has its own brutal arithmetic. If you start from a light seed, the remnant of a first-generation massive star, perhaps a few tens or hundreds of solar masses, then you need repeated, efficient accretion over a short cosmic interval to reach the masses some early systems imply. And efficient accretion is not something the universe gives away freely. Radiation from the feeding black hole pushes back. Gas supply becomes unstable. Feedback can choke the inflow that growth depends on. The timeline is narrow, and the object is hungry inside it. Some recent simulations have pushed back against the most pessimistic reading of this problem. A 2025 Nature Astronomy study reported that light-seed black holes in high-resolution cosmological zoom simulations could, under the right dense early conditions and with a revised seeding prescription, grow enough to dominate the progenitor population of later supermassive black holes. That does not solve every early case, but it matters because it shows that even a seemingly impossible growth story may not require exotic seeds in every scenario. But notice what that reassurance really means. It does not make the early universe more ordinary. It makes it more extreme in a different way. If light seeds can grow that efficiently, then the environments around them must have been exceptionally favourable. Dense gas, sustained inflow, rapid fueling, and a surrounding structure already competent enough to feed the engine without tearing the process apart too quickly. In other words, the black hole story loops back into the same deeper pattern we have already been tracing. Prepared halos, violent gas supply, early organisation. The black holes do not sit outside the crisis. They intensify it. Some objects did not merely arrive early. They seem to have begun with an advantage. That line is the real emotional core of this section. Because a supermassive black hole in the first universe does not just feel early, it feels ahead of the stars around it, ahead of the host galaxy's apparent maturity, ahead of the timescale our intuition wants to grant. The little red dots now being studied so intensively in the JWST era have only sharpened that feeling. A subset may be obscured, rapidly accreting black holes whose existence could illuminate how overly massive black holes appeared so soon after the Big Bang. The observational interpretation is still under active debate, but the pressure point itself is unmistakable. And that is why early black holes are more than an additional mystery. They are a convergence point. They touch the same hidden scaffolding as the early galaxies, because they need environments and gas supply. They touch the same timing pressure as the Hubble tension, because they are another way the first universe seems to outrun its expected schedule. They touch the same philosophical wound as the whole script, because they make the young cosmos look less like a place slowly learning to organize, and more like a place capable of concentrating power almost immediately. Still, caution matters here more than ever. It would be dishonest to narrate these discoveries as proof that black holes formed before galaxies in any settled sense, or that every strange red compact source is a supermassive black hole, or that cosmology now requires primordial black holes as the default answer. Those are possibilities at the edges of current discussion, not conclusions the field has secured. The responsible reading is narrower and stronger at the same time. JWST is finding enough early accreting black holes and enough candidate pathways toward very rapid black hole growth that the problem can no longer be dismissed as a fringe oddity. And once that is true, the whole first universe starts to feel slightly reweighted, because now the issue is not just that matter formed stars quickly, it is that some of that matter may also have built gravitational engines capable of dominating their environments with startling speed. A galaxy that forms fast is impressive. A black hole that grows fast is coercive. It changes everything around it. Radiation fields, gas inflow, feedback, quenching, the evolution of the host itself. In that sense, early black holes are not passive anomalies. They are amplifiers. They make the surrounding universe less innocent. Which means the deepest question is no longer simply how these objects formed. It is whether their existence is hinting at something more general, not a few exceptional pathways, but an opening universe whose effective rules, conditions, or energy budget made rapid organization easier than our later world intuition ever wanted to believe. And once you ask that question cleanly, you are forced into the next descent. Not toward another object, not toward another survey result, toward the possibility that the early universe was not governed by different laws, exactly, but by different dominant conditions, different pressures, different opening terms in the cosmic story than the simplified version we learned to trust. And this is the point where the temptation to say different laws becomes strongest and should be resisted. Because the most serious version of this story is not that physics failed in the dawn of time, it is that the early universe may have been governed by the same underlying laws we trust now, while living under a different balance of dominant conditions than the simplified narrative we learn to carry in our heads. That distinction is everything. A law is the rule, a condition is the regime in which the rule expresses itself. Water obeys the same equations whether it drifts as fog, falls as rain, or cuts rock as ice. The law does not change, the world it produces does. Cosmology may be facing something like that now. Not a universe with new grammar at every sentence, but a first chapter written under pressures, densities, backgrounds, and energy contributions that made the opening move faster, harsher, and more structurally effective than our later universe intuition ever wanted to believe. That is the safest radical thought. Not that physics was different, only that the early universe may have been living inside a different dominant structure. This is why ideas like early dark energy are so interesting to serious researchers, not because they are exotic in a cinematic way, but because they are disciplined attempts to alter the early cosmic bookkeeping without tearing up the whole framework. In these models, an additional energy component contributes non-negligibly for a limited period in the early universe, and then fades, changing the expansion history around the epoch that matters for the Hubble tension, while preserving much of the later successful cosmology. The appeal is not just that such models can relieve the expansion rate disagreement. It is that some studies have found they can also ease part of the pressure coming from Webb's bright, early galaxy population. One 2024 analysis concluded that an early dark energy cosmology could reproduce the observed ultraviolet luminosity functions at high redshift more naturally than baseline lambda CDM in the most extreme regimes. while also easing the Hubble tension that motivated the idea in the first place. That does not make early dark energy true. It makes it legible, and legibility matters in a scientific crisis. A good explanatory candidate does not merely fit a datum. It creates a corridor through multiple discomforts at once. It tells you how two cracks might belong to the same wall. That is why these models draw attention. They do not ask us to abandon the Big Bang, abandon gravity, or pretend the standard cosmological model was a fantasy. They ask something more surgical. What if the expansion history in the young universe carried an extra term, brief, real, and now mostly gone, that altered the timing of everything downstream just enough to leave both the Hubble tension and some early structure observations less strained? But even here, discipline matters. The existence of a compelling bridge is not the same thing as crossing it. Early dark energy remains one family of proposals among several, not a settled replacement for lambda CDM. The Planck legacy results still describe the 6-parameter standard model as an excellent fit to the cosmic microwave background, which is precisely why any amendment has to fight for room rather than being welcomed as rescue. A theory does not earn seriousness by being exciting. It earns seriousness by surviving contact with the full sky. And that is why the deeper shift here is philosophical before it is revolutionary. Once you admit that conditions can be the true source of the discomfort, the whole mood of the story changes. The early universe stops feeling like a simpler version of the one around us. It becomes a more extreme phase space, denser, more compressed, more causally unforgiving, more capable of turning slight advantages into overwhelming ones. In that kind of regime, familiar laws can produce unfamiliar tempos. Halo growth that is statistically allowed may become observationally dramatic. Gas supply that would later be self-limiting may briefly become ruthless. Black hole seeds that look insignificant on paper may find themselves in environments so violent and well-fed that they begin to dominate before the rest of the cosmic narrative has found its footing. The insult, then, is subtler than we misunderstood the universe. It is that we may have understood the laws and still misunderstood the mood in which those laws first operated. That is a harder thing to admit, because it is not the relief of error. It is the humiliation of oversimplification. We like beginnings to be clean. We like the opening of the universe to behave like an introduction, sparse, legible, patient, still gathering itself. That story flatters the human sense of sequence. Webb has been teaching a colder lesson. The first cosmos may have been lawful without being gentle, constrained without being slow, and intelligible without being narratively kind. The latest broad reviews of the first billion years emphasize exactly that transformed atmosphere, not the death of cosmology, but a new landscape in which early galaxies, early black holes, ionization history, masses, morphologies, and environments are all being remeasured under much more severe empirical pressure than before. And once you see the problem in those terms, an important simplification disappears. The question is no longer whether the universe broke the rules. The question is whether the rules were playing out inside a first act whose dominant pressures we summarize too cleanly. That opens the door to many possibilities without forcing premature loyalty to any one of them. Perhaps the shift is mostly astrophysical, unusually efficient star formation in dense halos, violent gas supply, suppressed feedback, a bias in how we turn light into mass, or a combination of all of these. Perhaps some cosmological extension, like early dark energy, is part of the answer. Perhaps the truth is mixed. A small revision to the background expansion history, amplifying a larger revision in how matter exploited the earliest halos. The field is not yet at the point where a single elegant sentence can replace the old one, but it is very much at the point where the old sentence no longer feels sufficient. That insufficiency is the real discovery. Not a new particle, not a new law, a new level of discomfort with the story's opening conditions. And that is why the next descent has to widen one last time. Because once the early universe becomes a competition between possible hidden terms, altered pacing, and unfinished explanatory bridges, cosmology enters its most difficult state, the moment when many theories become plausible enough to matter, but none has yet earned the right to feel inevitable. That is when a scientific crisis stops looking like collapse and starts looking like a crowd of doors in the dark. And the hardest part is this. Every door seems to solve something. None of them solves everything. That is what real theoretical pressure feels like. Not one dramatic replacement marching in to rescue the field, but a set of competing possibilities, each elegant at first glance, each costly on closer inspection. The current literature around JWST's early universe results reflects exactly that atmosphere. The standard model still fits an enormous amount of data extremely well, but researchers are actively testing whether tensions around early galaxy assembly and the Hubble constant point to revised astrophysics, modified dark sector behavior, or some combination of both. One path says the problem is mostly in the visible layer. Maybe the universe did not need a new cosmic ingredient. Maybe ordinary matter simply behaved more violently than we expected in the earliest halos. Gas may have cooled fast, collapsed hard, and formed stars with an efficiency that later cosmic history taught us not to expect. Feedback may have been less successful at shutting those first furnaces down. The mapping from light to stellar mass may still be too crude in some of these regimes. Under that view, the universe is not fundamentally stranger than we thought. It is just harsher in practice. The rules stay the same. The early environments were more ruthless. Recent reviews of the first billion years lean heavily on exactly these astrophysical uncertainties. Star formation efficiency, feedback, halo occupation, dust, morphology, and black hole contamination remain central to interpreting the most provocative JWST systems. That explanation has a certain dignity. It preserves continuity. It says the cosmos did not hide a new force in its opening act. It only lived through a regime where familiar laws produced less familiar outcomes. In some ways, that is the most conservative answer available. It is also emotionally unsatisfying, because once enough tensions gather, the astrophysics was messier than expected begins to feel like a phrase that can mean almost anything. It may still be right, but a theory starts to lose emotional authority when every surprise can be explained only by saying the small-scale details were more extreme, more efficient, more bursty, more obscured, more biased, more environment-dependent than anticipated. The danger is not that this is false. The danger is that it can become too elastic. And elasticity is not the same as understanding. So another door opens. Perhaps the issue is not only what baryons did inside halos, but what the background cosmology was already permitting before those halos ever formed. That is where early dark energy became so compelling. Not because it feels radical, but because it is specific. It modifies the early expansion history for a limited window, then recedes, offering a possible way to ease the Hubble tension, while also making the earliest luminous structures less strained. Recent work has argued that early dark energy can improve the fit to some JWST high redshift galaxy, results more naturally than baseline lambda CDM, while interacting dark energy models appear less favoured in that same context. That is the kind of idea a field reaches for when separate discomforts begin to rhyme. Because it is one thing to patch a local anomaly, it is another to find a revised background story that lets multiple anomalies breathe at once. But then the price appears. Any amendment to the early universe has to survive the most merciless witness in cosmology, the microwave background. Planck still stands as a towering success for the 6-parameter lambda CDM model, and that means every alternative has to thread a narrow corridor. It must relieve enough pressure to matter, without spoiling the precision structure the standard model already gets right. That is why no replacement has yet achieved inevitability. The old model remains too successful to discard casually, even as newer data force people to test what lies beyond it. So the field keeps widening the search. Maybe dark matter itself is less passive than we assumed. Maybe the dark sector interacts in ways that alter structure growth. Maybe the relevant change is not dark energy at all, but some modified perturbation history, some hidden coupling, some altered early balance that leaves later success mostly intact while reshaping the dawn. Theoretical work now spans exactly that landscape, from early dark energy to interacting dark energy scenarios to broader, beyond lambda CDM thinking driven by accumulating tensions rather than a single clean contradiction. And this is the moment where weak storytelling usually ruins everything. Weak storytelling wants a winner too soon. It wants to tell you which door is correct, which bold new theory is waiting to replace the old one, which elegant tweak will make the cosmos whole again. But reality is almost never that courteous. A living scientific crisis is not a revelation scene. It is a sorting scene. Ideas accumulate. Some gain temporary grace. Some solve one tension and worsen another. Some look brilliant until they meet the CMB. Some survive the CMB only by doing too little elsewhere. Some turn out not to explain the data so much as rephrase the discomfort. A paradigm does not collapse in one motion. It loosens through competing replacements. That is the real drama now. Not the destruction of cosmology, the multiplication of plausible incompletions. And there is something quietly severe about that state of affairs. It means cosmologists are no longer standing inside one clean explanatory corridor. They are standing in a chamber where several corridors now exist, and none has yet earned the right to feel like the natural continuation of the map. The standard model is still there, still powerful, still explaining more than any rival. But it now coexists with a growing readiness, even in mainstream scientific discussion, to imagine a more complex dark sector, a more intricate early expansion history, or a more physically extreme first billion years than the old narrative made emotionally easy. That shift matters because it changes what counts as conservative. Once, the conservative instinct was simple. Trust lambda CDM. Wait for better data. Expect the anomalies to soften. Now the conservative instinct is harder to define. Is it still more conservative to defend the old model with increasingly aggressive astrophysical tuning? Or is it more conservative to allow that a small extension of the dark sector may be less contrived than endless local adjustments? There is no final answer yet, but the fact that the question can now be asked without sounding unserious tells you how far the atmosphere has changed. This is what a field sounds like when it has stopped dismissing discomfort and started metabolizing it. Door after door were none fully open or none safely closed. And yet there is one more layer to the crisis that matters even more than the theories themselves. Because behind every model, every fit, every revised parameter, there is a human event taking place, one that science rarely shows cleanly from the outside. What does it actually feel like when a successful picture of the universe begins to lose its emotional smoothness? Not in public catastrophe, but in the private mind of the people who built their careers inside it. It does not feel like the movies. There is no single night when the equations fail dramatically on a glowing screen. No conference hall where someone stands up, announces the old universe is dead, and watches a century of cosmology fall apart before lunch. Science is almost never merciful enough to provide that kind of theatre. What it gives instead is slower, more difficult, and in some ways more intimate. At first, it feels like irritation. A discrepancy that should have gone away does not go away. A result that looked noisy starts surviving. A telescope built to refine the picture keeps returning details that make the picture harder to narrate cleanly. None of this is enough, on its own, to justify surrendering a successful framework. But something changes in the emotional life of the field. The model still works. The papers still get written inside it. The simulations still run. The language of standard cosmology remains the default grammar, and yet a quiet reweighting begins. Researchers stop asking only whether the anomaly is real. They start asking what kind of revision would be least painful if it is. That is not collapse. It is the first psychological concession. For the people closest to the equations, discovery often arrives as loss first. Loss of smoothness, loss of explanatory comfort, loss of the feeling that one story is sufficient. That matters because cosmology is not a loose collection of curiosities. It is a synthesis. People do not build careers in it by memorizing disconnected facts. They build them by trusting that the large pieces fit together in a way that is both mathematically powerful and emotionally coherent. The standard model has earned that trust more honestly than almost any grand theory in science. Planck's final result still describes 6-parameter lambda CDM as providing an excellent fit to the microwave background, which is one reason the field has treated it not as a convenient approximation, but as a genuine backbone. So when strain appears, the first reaction is not excitement. It is defense. Not dishonest defense, usually the opposite. Careful scientists are trained to distrust novelty before it earns the right to matter. They know how many strange results die under better calibration, wider surveys, stronger spectroscopy, cleaner modelling, or the simple humiliation of more data. That skepticism is not weakness. It is the immune system of the field. It protects cosmology from becoming a graveyard of fashionable errors. But an immune system can become exhausted. Not because skepticism fails, but because it keeps doing its job and the discomfort remains anyway. That is what makes the present moment so unusual. The Hubble tension has survived years of refinement rather than dissolving under it, including Webb's independent checks on the local distance ladder. NASA's own reporting frames this explicitly by tightening Cepheid measurements with Webb. The easy explanation that the tension was just a Hubble measurement artifact became less persuasive. And on the galaxy side, the field has moved past the first wave of sensational claims into a harder phase of sorting, revising, and still finding enough early luminous structure to keep the question alive. The best recent reviews do not read like panic. They read like a community being forced into precision without the relief of quick dismissal. That is what a real scientific crisis feels like from the inside. Not a revolution in public, a narrowing of innocence in private. People begin to talk differently. The old model is still spoken with respect, but less with ease. Words like tension, efficiency, incompleteness, beyond lambda CDM, and opening conditions start appearing not at the fringe, but in mainstream review language. Researchers still defend the standard picture where it deserves defending, because it still deserves it, but they stop defending its emotional smoothness. That is the deeper threshold. A field can survive unresolved problems for a long time. What changes everything is when enough serious people begin to feel that the old story may remain broadly true while no longer feeling narratively natural. And that feeling is heavier than outsiders often realize. Because if you have spent years building simulations, calibrating models, deriving intuition, teaching students, or writing papers inside one cosmological grammar, then any real crack in that grammar is not merely technical, it is autobiographical. It reorganizes your sense of what your work has been part of. The history of science is full of this quiet violence, the moment when a successful framework does not collapse, but ceases to feel complete to the people who know it best. The universe has not betrayed them. It has just stopped simplifying itself on their behalf. That is a subtler kind of wound, and yet it is also one of the reasons science remains beautiful, because the best researchers do not protect themselves by refusing discomfort forever. They adapt. They let the strain become method. They begin checking the old assumptions more aggressively. They ask where the flexibility ends. They test whether the model can still explain the data without becoming too elastic to remain explanatory. They explore alternatives not because they are seduced by novelty, but because the burden of seriousness has shifted. The recent theoretical literature around Webb-era cosmology shows exactly this behavior. Not chaos, not surrender, but an expanding willingness to test early dark energy models, altered dark sector behavior, revised baryonic efficiencies, and other routes through the current maze of pressure. This is why the phrase "scientists were wrong" is so shallow here. Wrong about what? Wrong to trust a model that explained an enormous range of observations with rare power. No. Wrong to treat that model as final. Perhaps. Wrong to feel the early universe had become too legible. That is closer. Because that is what Webb has really disturbed. Not only measurements, but composure. The field still has equations. It still has predictions. It still has a standard model that outperforms every full replacement. What it may no longer have is the old emotional permission to believe that the first universe was already understood in the right tone. And tone matters more than it sounds. A theory is not just a list of outputs. It teaches researchers how reality is allowed to feel: gradual, hierarchical, statistically natural, cleanly connected from relic radiation to late-time structure, when enough new evidence begins to rub against that feeling. The scientific response is not instantly to abandon the theory. It is to endure a period where the theory still works, but works under a growing shadow of insufficiency. That is where cosmology seems to be now. Not in ruin, not in triumph, in a state much harder to dramatize and much harder to survive. A successful picture of reality becoming emotionally rough at the edges. And once that happens, one last change becomes possible. Perhaps the strangest change in the whole story. Because a universe that organizes itself this quickly, this efficiently, this early, is not only a threat to cosmological comfort, it may also be a universe unusually capable of building chemical complexity, planetary structure, and the preconditions for life far earlier and more widely than our older intuitions would have guessed. And that possibility does something unexpected to the emotional balance of the story. Up to now, a faster, harsher, more efficient early universe has felt mainly like a threat a threat to cosmological confidence, to the smoothness of the standard timeline, to the sense that the opening of reality was already narratively settled. But the same pressure points that make the universe feel less comfortable may also make it feel more fecund. A cosmos that organizes matter quickly does not only build galaxies sooner, it may also build chemistry sooner, complexity sooner, and the conditions for planetary history on shorter timescales than our older intuitions encouraged us to imagine. Webb's broader science program explicitly ties together early structure, heavy element enrichment, and the long search for habitable environments beyond Earth. That does not mean Webb has found life. It means something more disciplined and perhaps more beautiful. The same universe that seems capable of producing luminous structure early is also the universe in which stars begin forging the elements life depends on: carbon, oxygen, sulfur, iron, silicon. None of them are primordial gifts lying around in finished form. They have to be made inside stars and scattered through violence. A young cosmos that forms stars rapidly also begins manufacturing chemical possibility rapidly. The first billion years, according to JWST, is not only a story about unexpectedly early galaxies and black holes, it is also a story about chemical composition, enrichment, and the speed with which the universe stopped being chemically simple. That matters because life is not built out of wonder. It is built out of leftovers, out of stars that lived, burned, exploded, and contaminated the dark with complexity. Every rocky surface, every atmosphere, every ocean, every carbon chain, every mineral scaffold for later biology is downstream of that ancient enrichment. So when Webb suggests a universe that may have become structured with unnerving speed, it is also hinting at a universe that may have started preparing the raw conditions for later habitability earlier than the older, calmer emotional picture allowed. That is not a claim about biology itself. It is a claim about readiness. And here, of course, is where the script has to become more honest, not less. Because the modern search for life is exactly the kind of topic that attracts false transcendence. One suggestive molecule, one atmosphere, one headline, and suddenly people start narrating destiny. Webb deserves better than that. The telescope has indeed transformed exoplanet science, and NASA describes it as a major tool in the search for habitable environments by reading atmospheric chemistry from starlight passing through alien skies. But that is not the same as having crossed the threshold into detection of life itself. The clearest example is K218b. Webb's observations did reveal methane and carbon dioxide in the atmosphere of this sub-Neptune world, and NASA's release framed those detections as important because they are consistent with the possibility of a hydrogen-rich atmosphere above a water-ocean world. Depending on the planet's true nature, that is already extraordinary. It means Webb can read the broad chemical weather of a world 120 light-years away and say something real about its atmospheric composition. But the more dramatic claim, the idea that dimethyl sulfide might be present as a biosignature, remains tentative and unresolved. NASA's own language on the original result called it a possible detection, and later work arguing for DMS and / or DMDS at around 3 sigma significance, still explicitly says more observations are needed and that abiotic sources and molecular cross-sections need further scrutiny. That caution is not a disappointment. It is the proper shape of awe. Because the real miracle is not that Webb has already found aliens. It has not. The real miracle is that we are now at the stage where the atmospheres of distant worlds can enter the same intellectual frame as the dawn of galaxies and the opening of cosmology. One instrument is forcing us to reconsider the timing of the first universe while also letting us test, molecule by molecule, whether later worlds carry the signatures of chemistry that might matter for life. NASA's 2025 overview of Webb and the search for life makes exactly this point. The telescope is opening the era of atmospheric characterization for potentially habitable worlds, but interpretation remains difficult and demands repeated, careful observation. And that is why this matters so much for the larger argument. A universe that organizes itself efficiently is not only more destabilizing, it is also more generative. More able to make stars, more able to enrich gas, more able to produce planets, more able, perhaps, to create chemically promising worlds earlier and more widely than our older emotional story suggested. Not because life is easy, nothing in the evidence allows that claim. The path from chemistry to biology may still be extraordinarily rare, contingent, or fragile. but the stage on which that path could even become possible may have been built faster than we imagined. The same harshness that unsettles cosmology may widen habitability's raw preconditions. There is a severe beauty in that. The universe may be less narratively comfortable than we thought, and more generous in material possibility at the same time. That combination is stranger than either hope or dread on its own, because it means the crisis Webb has opened is not merely a story of broken expectations. It is also a story of enlarged horizons. A cosmos that formed structure early is not simply a cosmos that embarrasses theory. It is a cosmos that may have begun laying down the conditions for later complexity with astonishing speed. The first violent generations of stars may have accelerated not only the architecture of galaxies, but the long chemical preparation for worlds, atmospheres, and perhaps eventually minds capable of looking back. And that turns the whole emotional charge of the script. What first appeared as a threat to understanding starts to look like a deeper kind of invitation. Not reassurance, not sentimentality, something colder and larger. A universe that did not wait for our intuition to catch up before becoming complicated. That may be the most important shift of all, because once you stop demanding that reality unfold at a pace the human mind finds narratively fair, you begin to see Webb's discoveries in their full shape. The telescope has not simply found anomalies. It has revealed a cosmos whose opening chapter may have been more efficient, more compressed, more chemically productive, and less psychologically obedient than the version we learned to trust. And that is why the ending cannot be a summary. It has to return to the first wound, to that first image in the dark, to that first impossible-seeming maturity, to the feeling that the universe, when finally seen clearly enough, did not look younger than expected. It looked as though it had already moved on without us. And that is the part that lingers. Not any one galaxy, not any one tension, not even any one theory waiting in the wings. What lingers is the change in posture. At the beginning, the universe looked like something we had almost learned how to tell cleanly. There was a chronology to it that felt earned, a hot beginning, expansion, cooling, darkness, the first stars, the first galaxies, gradual structure, later complexity. The story was not childish. It was one of the great achievements of human thought, but it carried a hidden comfort all the same, the belief that if we looked far enough back, reality would become simpler in exactly the way our intuition wanted simplicity to look. Webb has not destroyed that story. It has done something more difficult. It has shown us that the story may have been true in outline and still too gentle in tone. That is the real wound in all of this. The telescope did not find a universe that is chaotic, or lawless, or eager to mock science. It found one that may be more exacting than our summaries, one that can obey deep rules and still produce beginnings that feel prematurely advanced, structures that seem too ready, black holes that seem too hungry, and a chronology that no longer sits inside the mind with the same smoothness it once did. The universe has not become less lawful. It has become less obedient to our summary of it. That is the matured form of the opening promise. We began with an image that seemed to arrive too early, a patch of darkness filling with objects that did not look like the infancy we expected. But the deeper meaning of that image was never visual. It was moral, almost in the scientific sense of that word. It asked whether reality is under any obligation to unfold at a pace that feels narratively fair to the creatures describing it. And the answer seems to be no. No obligation to appear unfinished when it is young. No obligation to make the first billion years emotionally legible. No obligation to let our favourite model keep its elegance untouched once a sharper instrument arrives. That answer is not anti-scientific. It is the reason science matters, because science is one of the only human activities willing, in the long run, to give up a satisfying story for a truer one. Not immediately, not gracefully, not without resistance. But eventually. That is what is happening here. Webb did not hand us a replacement cosmology wrapped and waiting. It handed us a harder universe and forced our confidence to become more adult. And adulthood, in science, is not certainty. It is the ability to remain inside a world that has become less comfortable without retreating into fantasy. That is why this moment matters so much. Not because we can finally say cosmology has failed. We cannot. The standard model still stands on extraordinary success. Not because we can finally announce a new theory. We cannot. The doors remain open, but none has yet earned inevitability. It matters because the emotional contract has changed. The old map is still powerful, but it is no longer experienced as closed. The dawn of the universe has opened again. That alone is a rare event in the history of thought. For a while, modern cosmology had achieved something almost impossible. It made the origin of a large-scale structure feel nearly domesticated, not solved in every detail, but bounded, narratable, a grand mystery under control. Webb has reopened the texture of that mystery without cheapening it. It has not pushed us backward into ignorance. It has pushed us forward into a more difficult knowledge. A knowledge in which the first universe may have been more efficient than expected, more compressed than expected, more chemically productive than expected, more structurally prepared than expected, and therefore, in the deepest sense, more different from our intuition than expected. That phrase, a different universe, is easy to misuse. It can sound like clickbait metaphysics, as if Webb had discovered another set of laws hiding behind the visible one. But the more serious meaning is harder and far more unsettling. It may be the same universe, just seen without the comfort we had projected onto its beginning. Seen before our summaries had time to soften it. Seen before the narrative caught up with the mechanism. Seen at the moment where lawful reality stops feeling familiar. That is why the first image matters so much even now. A dark field, ancient light, tiny red structures suspended at the edge of time. At first they looked like objects, then they became histories, then budgets, then tensions, then leverage against an entire chronology. By the end, the image is no longer a photograph of distant galaxies. It is a photograph of the limit of human intuition. We looked into the dark expecting to witness the universe becoming... What Webb may have shown us is that, in crucial ways, it had already become far more than we were prepared to permit. And there is something almost tragic in that. Not tragic because the universe is cruel, tragic because it is indifferent to the storytelling needs of the minds trying to understand it. It does not slow down so the pattern can feel fair. It does not arrange its first chapter so the later reader can feel clever. It does not preserve our composure as the price of being knowable. It simply is. Dense, expanding, gravitational, radiant, violent, fertile, lawful, strange. And if Webb is teaching us anything at the highest level, it is that truth in cosmology does not always arrive as simplification. Sometimes it arrives as an increase in structure, in tension, in implication. Sometimes the better instrument does not make the universe easier to summarize. It makes summary itself look premature. That is the afterimage this story should leave behind. Not that science is broken, not that everything was wrong, not that mystery has replaced knowledge. Something more severe. That our deepest models can be powerful, elegant, and still not yet equal to the full character of reality. Which is why the most honest ending is also the least comforting. The James Webb Space Telescope did not merely look deeper into space. It looked into the part of reality where our confidence had become too smooth. And what came back was not chaos. It was something harder to live with. A universe that still makes sense, but no longer in the order, pace, or emotional shape we once believed it would.